Okay, this video is a walkthrough of a reference that we put up on the Canvas page for System Verilog. And so I wanted to point out some highlights in the first few pages. I want you to go ahead and get started in reading this document, but let me point out some things that hopefully will be useful. One of the things that I'd like to say about it is that there's System Verilog, there's Verilog, and it's been sort of an evolution. And so it has a line here, Systems Verilog is the most recent version of Verilog. Okay, and so there's references about System Verilog, and then the next line in the document says, unfortunately, System Verilog references you find on the internet assume that you know Verilog, but then Verilog came first, and so Verilog references don't include information about System Verilog. So it makes it a little more complicated to learn something that's big and powerful and can do a lot of things. You know, where do you start and how do you best proceed in learning these things? And so it's hard to learn every little detail as you know before you move on. And so what we try to do is give you some Verilog assignments, and then you pick up stuff along the way. All right. So one of the first things that I wanted to emphasize that Verilog is a hardware description language, so you should start learning some of these acronyms, HDL, hardware description language. And you can build out different types of hardware. We use the FPGA boards that we have in the lab, the Basis 3s, so you can program the hardware connections. Here's another term you should know the acronym for, FPGA, Field Programmable Gate Array. And so these are things we're trying to pick up. All right, now the next thing I wanted to emphasize, and we'll talk about this a lot, because it's a hardware description language, the code in Verilog is not executed sequentially line by line like you would a typical programming language where one instruction happens and then the next instruction happens and so forth and so on. Because we're describing hardware, think of it this way: if you had like 4 chips laid out, all right, and you're trying to use that hardware, you have to list one of them first, but all of them are working at the same time. And so the language, the description that you have for that somehow has to keep that in mind. All right, and so that's what's going on with any hardware description language, is you're modeling different parts from hardware, and you keep in mind that they all work at a given time instant. So in a way, things are happening in parallel, not sequentially like a typical programming language. Okay. The next thing I wanted to show you is that there are links in this document, and like this first one about System Verilog, you can click on a link here, and it tells you more details than you probably can digest on some of these links. But I just wanted to make you aware that those are possibilities as well. Okay, so back to this reading assignment. So Verilog can be used in a number of different ways, and we'll be talking about this as we go. There's behavior modeling, and then there's this list here says gate level modeling, transistor level modeling. Typically, we don't get down into the gate level and transistor level because it's too tedious. We need higher level models, and Verilog lets us do that. A big part of hardware description languages is that they have a simulation capability that lets you see if your hardware is doing what you expect it to do. All right, and then what's not on this list that probably should have been is, but once you have your description, you can actually synthesize that into gate connections that get implemented on some type of target hardware. Now, we're going to learn that not everything you write in Verilog is synthesizable, and we'll have to figure out what that means as we go. All right, so next thing here is there's a list of references. You can look at this chipverify.com. They have lots of good things, and you can click on here and you can see there's different levels of, how is Verilog useful? Different levels of tutorial to help you learn about Verilog. So I encourage you to explore that, to hopefully you're interested and want to learn more, and you can dive in there. But take it small bites at a time. Another thing that's useful is a quick reference guide if you're wondering about syntax of things or different reserved keywords and things that you need to know whenever you're trying to implement something in Verilog. This document has things, relatively condensed down into one place where you can see things like reserved keywords and just, reference material about Verilog. Okay, so be aware of that. And there's some other examples, FPGA programming type by Verilog examples. All these things are useful as we start to explore Verilog. All right, so the next thing I want you to do is, as you read this, start trying to digest what are the basics. And we've already talked about the idea that Verilog is going to be implementing things using modules. Okay, so modules are our basic building block. You can read here some examples of how that goes and how some of the syntax works and some of the calling conventions for modules. All right, next I want you to be aware of the data types that we're going to be used right away. For now, the most important ones are, we have a wire data type. Think of it like a physical wire where it's connecting to something, and output connects to an input, and so forth and so on. And these are continuously driven by some output. So if you envision that, you'll see, you'll come across situations where you can say, oh, I can't do that because I can't have a wire that's connected to two different things. And so as you write your code, if you visualize it as a wire, you tend to make less errors. Okay, the next thing that we're going to do, we've talked about this in class, registers. Registers are used to store inputs or store the values of outputs. Okay, so it's like a memory. We haven't talked a lot about memory yet, but you're going to use registers when you make test benches, and test benches are the subject of Lab 3. Okay, there's some warning here in the text about, you should declare wires before you use them, and it gives an example of how things can go wrong. Let's start wrapping our head around logic values too. We know about zeros and ones, but there's also a couple of other values that we will have in Verilog. And it gets a little confusing because we're going to use the character X for when we do K-maps. But in Verilog, 0 and 1 mean what we think, all right? And then Z stands for a high impedance state. So if you think of a high impedance state, if you had a wire with a big resistor connected between, one connection point and another connection point, if that resistor is really, really large, it models an open circuit. Okay, so high impedance would be like not connected. All right, and so sometimes we will want to have logic elements that either work, 0 or 1, they're taking on different logic conditions, or we might want to have that part of the circuit effectively disconnected. So if we can drive that into a high impedance state, by the way we configure the silicon, that's good too. And so Verilog has a way of modeling that. Okay, another thing that will happen is so this is especially true when you're doing simulations. When you start a certain process, sometimes certain variables aren't yet defined. It takes a while for your design to instantiate things and assign values. And so during these startup times, you'll see X's or red signals in your Bravado signal displays. The high impedance states are blue signals. So the color coding there is significant. Okay. From there, I'd like you to start reading about, literals and constants and our format for representing values. We're going to just jump into some example code and run through this so that you can see this working. But it's always good to be able to go back to our reference. So, the first, page 4 through 7, I think, starts working you through different types of operators and conventions for listing inputs and outputs and so forth. All right, so read through this. Follow these links. You can take a look at different links, and it gives you more detail. For example, I click on this link, and it shows a simple combinational logic circuit. We're going to be doing that in Lab 3. And so you can learn from there. All right, so that's part of the Lab 3 work, is to explore this, read the first 7 pages of this document that we're posting up on Canvas, and take the time to explore some of these things.